and discovered pulsars. And at the time, they were the hold on, I've got my last slide up. This is going to be, how am I going to do this? Right. Let's go back to, there we are, that looks a lot better. Yeah, okay, so I forgot what I was saying now. Anyway, I started off in radio astronomy, and at the time they were have the best radio telescopes in the world. This was back in the 1970s, and I've been in the group as a research student for 2 weeks, and the two professors, Ryle and Hewish, won the Nobel Prize, so I thought I probably was in the right place. But I discovered during that what I was really better at was not doing observations, but was doing the underlying physics. So that's really what I've spent my lifetime doing, the underlying physics. But once you're doing physics, of course, then it goes off into other things. And so I spent half my life doing the physics of for astrophysics, and the other half doing the physics of when you zap things with high power lasers. So right at the end of this talk, as long as I don't run out of time, I will say a little bit about what we're doing with high power lasers that actually reproduces astrophysics in the laboratory. But most of the talk is going to be about astrophysics at the highest energies, and I should acknowledge my postdoc down there at the bottom of the page, James Matthews, who's now in Cambridge, who's been collaborating on quite a bit of this stuff. I'm at the University of Oxford. I'm also at the Rutherford Appleton Laboratory, if any of you know that, with the laser facility that's there. And as for that picture, which is a supernova remnant, we will come to later, but let's move on. Right, so if we're talking about the highest energy things in the universe, then we're talking about cosmic rays, high energy particles arriving at the Earth from somewhere out there. And my aspiration during my research career has been to find out how they get their energy and where they come from. Well, cosmic rays were discovered back in 1912 by Victor Hess, and you'll see on the screen a picture of him going up in his balloon. And he took up, as he went up, his gold leaf electroscope, which I at least remember from my school days having one of those. And it measures ionizing radiation. And he found that as he went up to higher altitudes, the amount of radiation he got was actually increasing rather than decreasing. And that meant that it was coming from outside the atmosphere. Now, he didn't know what it was, so he called it rays, and they came from outside, so they were called cosmic rays. And so that name has stuck, but it's a totally inappropriate name, but we are actually stuck with it now. There was another guy at the time called Puccini, an Italian, who actually made a very similar discovery at the same time. And he did the opposite thing. He went down under the ocean and measured what was happening and found the same effect, that it was height dependent. So they both actually discovered cosmic rays. But when it came to giving the Nobel Prize, Hess was still alive and Puccini had died, and you can't give a Nobel Prize to somebody that's died. So Victor Hess got the Nobel Prize and is well known for being the discoverer of cosmic rays, and poor old Puccini is rarely remembered. So the moral of that is, if you want to win a Nobel Prize, make sure you live a long life. Right, so to give you some idea of the energies involved. So these are energies in electron volts. It's better than doing degrees Kelvin or Celsius or Fahrenheit or something like that. But it's essentially a temperature and energy of each of these particles. And so starting at the top of the screen, room temperature is 1/30th of an EV. If you go and visible photons are about 1 EV. And then if you go up to KV, then you're talking about the X-rays that you do, going up factor of 1,000 every time. MeV, that's the energy of a relativistic electron. GeV is the energy of the mildly relativistic proton. TeV, another factor of 1,000 up, is the Large Hadron Collider formed in our galaxy. Then there's EeV, which I've put for significance that it's the amount of energy emitted by a light bulb in 1 second. And then you get up to ZeV, which is where the highest energy cosmic rays are. Right, and that's it with zeros after it, you see, just to impress you. And that's the energy of 1 proton, and that 1 proton has the same energy as a well-hit tennis ball, a single proton. So we're talking about quite remarkable energies here. Right, so these cosmic rays, which are mostly protons, arrive at the Earth, and this is the spectrum, a log-log plot, you see. So this is energy in electron volts, going from 10 to the 11 up to 10 to the 21. You see 10 orders of magnitude going across there. And we only start at about the same energy as you get with the Large Hadron Collider at CERN. And then you got a factor of 10, then there's a slight bend in it, and then there's what's called the ankle there. You can see, if you imagine a leg, that's the knee, that's the ankle, and that's the sort of toe down here. So we're talking about a massive range of energies, and yeah, where they come from is quite a challenging puzzle. Another way of trying to impress you about the energies is to look at their velocities. So the highest energy cosmic rays move at that fraction of the speed of light. They come to us from a very large distance, that number of meters, taking about 100 million years to get to us. And if from that distance a cosmic ray set off at the same time as a photon, it's going so fast that it only arrive at the Earth 10 meters behind the photon and a millionth of a second later. So these are extraordinarily high energy particles. Well, how do we detect them? Well, there is a basic difficulty here. So here is the spectrum. Here is the number of them that arrive per unit area and per unit time. And if you're talking about ones with the same TeV energies, but look at all these orders of magnitude. And when you get up to the highest energy, there are very, very few of them. And the rate at which these arrive is 1 per square kilometre per century, right? So it's pretty difficult picking these things up. And if you want to detect their arrival, then you have to have a very large detector, so many square kilometres, and you have to be very patient. And so it can be done, and it is being done. And there are 2 observatories in the world, both in the Americas, which do it. One looking at the northern hemisphere and the other at the southern hemisphere. The one at the bottom in the southern hemisphere in Argentina is actually the largest and the best one. Right, so it's just an array of detectors like this spread over a very large space of grassland. So this is the OJ one. It's actually headed up by, this was the brainchild shared between a guy in the US, but primarily by Alan Watson, who is British and works out of Leeds. So there's a lot of UK engagement in this. And so what it is, that's one of these detectors, and when cosmic ray comes in through the atmosphere, it turns into a shower of lower energy particles, and you collect these and measure the total energy, and that's how you know what energy came in. You could also do this thing which images the shower as it comes in, and that gives you more information about the direction it comes from. So they're spread over a large area near to a place, Malawi, in Argentina, which as you can see is quite close to the Andes, and it has an area which is 30 times the size of Paris. And if you do that, you can collect a few of these at the very highest energy, and quite a few at an energy smaller than that. So if you go above a certain energy, which we count as being the very highest energy ones, then each arrival is an event in itself. So this is a picture of the whole sky, and each of these dots is the arrival of one cosmic ray. And the blue ones are the ones measured by the Auger telescope. The red ones are in the northern hemisphere, measured and detected by the telescope array. And if you look at that, it looks pretty uniform. And so the hope of building the Auger telescope was that we'd see a lot of cosmic rays coming from a certain place, and then we'd know what the source was. So it's been a bit of a, well, it's a slight disappointment that they're spread so uniformly over the whole sky. And one of the problems, of course, is that when you send a charged particle across through large distances, there is a magnetic field there which can deflect it. But these should be coming pretty well straight, more or less, from where they're coming from. So it's really quite a mystery. But if you look closely, there's a radio galaxy, which I'll tell you about there, called Centaurus A. And if you have a look, there's some more dots around there than there are generally. So we're pretty sure there's a source there. And there is another sort of less obvious source, which I shall talk about. But there's not a lot of information there to tell you about where they're coming from and what kind of object gives them their energy. Right, so where do the highest energy cosmic rays get accelerated? Well, I've given you a slight preview of it. And right. So basically, there are very few objects in the sky which are big enough and large enough and have enough energetic enough that they can actually produce these cosmic rays, because you're getting up to these massive energies and they're quite strong constraints. And so there are other ideas, but the best idea, which we've been following, is they come from what is radio galaxies. Okay, so if you're not familiar with radio galaxies, this is the archetypal radio galaxy. It's called Cygnus A. This is a radio map made of it. And there at the center is the galaxy that's throwing out a very thin jet, which goes out a few hundred kiloparsecs into the intergalactic medium, runs into the small amount of the matter that is out there, gets stopped and gives these bright hot spots, and then flows backwards. And that's where we think it's all happening, one way or another. And that's the kind of telescope that measures it. That's very similar to the radio astronomy radio telescope that I started off in radio astronomy in Cambridge, although the VLA telescope in the US is now a few times bigger. But the Cambridge one was fantastic for its time and really world leading. But it looked like that, and what you do is you have a load of small dishes, and together those form a single dish, the equivalent of a single dish, the same size as the whole spread of the single dishes. But in terms of what's powering this thing, it's extraordinary. You get these thin jets, and how they're formed, we're pretty sure, well, we are sure, is that they come out of a black hole at the center of this galaxy, a massive black hole. This is, in this image of it, there's material spiraling around it and gradually falling into it. And then out along the axis of rotation, you get this highly relativistic jet, which is that, and turns into that. So all the activity in here, the black hole here is about the same size as the solar system. And that powers something which is many times the size of a galaxy. So it's really quite extraordinary. Here's another nice picture of a one of these radio galaxies. This one's called Hercules A. Quite a large distance away. Oh, is somebody writing on? I'm seeing some, right. Okay, I've seen some squiggly lines appearing, which maybe I've done. But anyway, never mind. There we go. Anyway, so here's the galaxy at the center. Here's the jets, and here's the interaction with the intergalactic medium. Right, so step back a bit. So it's basically things like that which we think are producing the highest energy cosmic rays. And this is a plot of the whole sky in radio at 408 megahertz. And that band there is the galaxy, the plane of the galaxy. And so you see there's a lot of radio emission coming from the plane of the galaxy. But there are also some particular sources here. Now I showed a picture of Cygnus A, and that's it just there. There are other radio galaxies called Centaurus A, M87 or Virgo A, same thing, Fornax A. And so they're the ones in white, so they're all outside our own galaxy. The ones in yellow are actually inside our galaxy, and they're the remains of supernova explosions. And so I'll come back to those later. But basically, these are the ones we're all interested in. You might notice that they all end up with A at the end. And what's the reason for that is that when radio astronomy was started out, they found one source, which was probably Cygnus A or Cassiopeia A, and then they found another, and so on. And always, so what they called them was they found a source in the galaxy. So Cygnus A is the brightest source in the Cygnus constellation, Centaurus A, brightest in the Centaurus constellation. Then you get Centaurus B and C, but then of course you find so many more that it all changes. But the name has been stuck, so they're always known as Fornax A, Centaurus A. The Crab Nebula is actually called Puppis A. Right, so there's two classes of sources we're really interested in. The white ones, which are outside the galaxy, which produce the highest energy ones, probably, and the yellow ones, which are inside our galaxy and produce lower energy ones. Right, so Virgo A, M87, NGC C4486. I remember on one occasion giving a similar talk to an astronomical society, and they told me that they can actually see Virgo A with their telescopes. So here's the galaxy, but they wouldn't be able to resolve the bright spot there. And there's some question about whether this jet coming out of it could be seen. But there is this very thin jet coming out of it, and that's actually taken by the Hubble Space Telescope. Another idea of how extraordinary this is, here is a compilation of radio observations of the Virgo A radio galaxy. Right, so on the largest scale, which is this, that's looking at the whole thing. The galaxy is in the middle here. If you take that bit there between those two white stars and blow it up, that's that bit. If you take, you can see the jets beginning to be seen. And if you take that part of it and blow it up, you get that. If you take that little square of it and blow that up, that's the Hubble Space Telescope image of it. And then you can take the bit right at the center, and with radio observations, you can still see that. So look at the range of scales there of jets powering this great big thing that's starting off on a very small scale. And if you've been watching your newspapers, you might have seen something about the wobbling black hole in M87. It's actually been the national press. There's this thing called the Event Horizon Telescope, which is a radio telescope that can actually focus and resolve what's happening close to the black hole. So this is that actually is the black hole. Now, you can't see the black hole because it's black, but what you can see is the stuff spiraling around it and gradually falling into it. And they've got a series of pictures of it over a period of time, and it started to wobble. It's not the black hole that's wobbling. The press calls it a wobbling black hole, but it's actually the accretion disk around it, stuff falling into it. But that's the size of the solar system, and that's what's powering this massive structure. Right, so that's M87. What other ones have we got? Well, I mentioned Fornax A and Centaurus A. This is a plot of radio megaparsecs, and this is their power. And what you want to see the cosmic rays is for it to be, the radio galaxy to be nearby and be powerful. So the three that stand out are M87, Fornax A, and Centaurus A, these three up here. And then this is a blow up of the cosmic ray sky. This is in galactic coordinates, and Centaurus A is where that yellow circle is, and the green circle is where you get a little bunch of cosmic rays come from. So the two are in the same place, and so that's pretty certain that we are actually seeing these cosmic rays coming from this radio galaxy Centaurus A. There's nothing coming from M87 that we can see, or Virgo A. Fornax A down here, which is at the center of this pink circle and allowing for deflection, that might be allowing for a bunch of cosmic rays which are coming down here. That Cygnus A one, which is the brightest of them all, is too far away at 180 megaparsecs, so we can't see it. So apart from the mystery, which I can tell you why it's not a mystery at all, of why M87 isn't producing them, we are actually seeing some signs that these cosmic rays are coming from these two nearby bright radio galaxies. Right, so here's a picture of what they look like in the radio. Centaurus A on the left, and Fornax A to the galaxy just there, and just there. And you can see these are massive things. I mean, so a parsec, I think, is 3 light years, if you like thinking about it in light years. But so what it looks like to us is that these giant lobes in the radio are stores of cosmic rays, and then the cosmic rays are leaking out of these reservoirs and coming to us. So that's our theory of how it's actually working. Right, so, but let's have a look at Fornax A. Many of you, I guess, are optical astronomers. That's a picture of Fornax A, pretty ordinary galaxy. I think those are dust clouds just there. You can probably tell me better than anybody. And then this is the radio superimposed. There's the optical picture of the galaxy in there, and there's the radio out here. Right, so that's Fornax A. Centaurus A. Well, this is the same idea. The orange there is the radio, and then you can see the optical in there a little bit. It looks like that, so you can see what looks like a fairly ordinary galaxy, but you see these little puffy jets coming out of it, but nothing absolutely impressive like the Cygnus A one. Those are very apologies for jets, really, and so it's obvious that it's not really very active at the moment, probably a lot more active in the past. But they're a fairly ordinary galaxy there, and probably, say, 20 mega years ago, something like that, there was a strong jet, and that produced all this orange stuff here, which now I see in the radio. Right, so if you look at Centaurus A and Fornax A, they're obviously in turned off state at the moment. They're not doing much, but maybe once they looked a little bit like Cygnus A. So that's what we're thinking. So in terms of understanding what's happening, then we go back to Cygnus A. And this is what I showed you a few moments ago. This is the radio. There's the galaxy. There's this fantastic jet powering out, and the power is I don't know whether that means anything to you. It just looks like a number, but that is an amazing power there, and the jet velocity is going to a good fraction of the speed of light. So that's what it looks like in the radio. This is an X-ray picture of it, and what you're seeing is hot gas here. They've got the same features, the galaxy at the center, these interaction points with the intergalactic medium out here. And what's happening with what we're seeing in the X-ray is hot gas. So what's happening is the stuff, lots of energy going out along the jet, stopping here, and then spreading out and heating up the surrounding area. And that's what we're seeing as hot X-rays. But what's really interesting about Cygnus A is if you have a look at the center of it. Right, so this is an optical picture here. There's the galaxy, and you'll see straight off that that's a rather strange looking galaxy. If you look at use the Hubble Space Telescope and focus in on that, you can see it looks like that. And that's a very strange looking galaxy. And what is thought is happening is the collision of two galaxies, and they've made a mess of each other. And there are probably black holes at the center of each galaxy, or at least one of them. Well, they all have black holes probably. And so there's stuff falling into the black hole. So there's a lot of energy released as all this material falls into these black holes as they either have merged or are merging. And that's the power source which sets out these large jets. But you can see that that's a real mess of a galaxy. What's happening there is not like a typical galaxy. It's probably two galaxies merging into each other, colliding. Right, for those of you who are, I put this in because I guess that some of you are particularly interested in how far you can take optical telescopes. Well, of course, the point of the Hubble is that you get above the atmosphere. But now you can do adaptive optics, and that's what's happened here. This is actually in infrared on the Keck telescope, and that is on the same scale pretty well as this picture here. But whereas that one's done from above the atmosphere, this is done from ground level, and you can see the scale there, 2 arc seconds, and the amount of resolution we get in there. And this is a real groundbreaking development over recent years about using adaptive optics. Right, okay, so that's so we're hoping that well, we've got good reason to think that Fornax A and Centaurus A looked a bit like Cygnus A a while ago. And then one asks oneself, how could this structure be producing very high energy particles, high energy cosmic rays? And what it comes down to is looking where shock fronts are. And there's loads of shock fronts around, and I'll come back to that in a moment. But James Matthews, who I mentioned, who's gone off to Cambridge now, but was working with me for a few years, did these computer simulations, sending out a jet, and then structures like this. These ones here are, you get 2 end points because the jet is waving around a bit. You don't see that here. You see the jet goes up and then it stops, and you get all this stuff coming back down the edges of the jet. This other picture here is not an astrophysical phenomenon. My wife and I were out one Sunday afternoon in the park at St. Cross Hospital at Winchester, and we sat down having a little rest as we do, and looked out over the water and saw this, and I thought, well, that looks like a radio galaxy. So we took this picture flow down there. Completely different physics, but it gives you an image of the kind of thing that's happening. Right, so I'll come back to shocks and how they accelerate particles in a few moments. But the problem with the trying to understand what happens from looking at radio galaxies is that they're a long way away, you've got limited observations, and things take a long time to change. So they're not so good for understanding what the basic physics is that's going on. So even though they don't get to such high energies, it's very fruitful. We've learnt most of our physics by having a look at what happens within our own galaxy. Right, so here we're not talking about the energy production by black holes at the center of galaxies. The basic source here is a supernova. Now, we haven't had in our own galaxy that's been observed for 100 years or even 300 years, although we know there has been one within 100 years, but basically we can't really see much of ones that have happened recently. But if you go out to the Magellanic Cloud, one of the dwarf galaxies going around our own galaxy, then there was a beautiful supernova in 1987. So this was 1987A. And so that's the dwarf galaxy. And that's a picture of the galaxy before the supernova. There's the star that went supernova. And that's the supernova explosion. And that shows you how the energy released from a supernova can be as bright as a whole galaxy seen to far into the universe. But that release of energy launches something which can then produce the high energy particles. Right, so you can look at one's supernova explosions that have happened in the last 1,000 years and see what remains of them. You might know of the crash in 1054. That's what you see now in the optical. If you have a look at in the X-ray, you can see the structure in the middle of that. So that's hot gas and energetic particles emitting synchrotron emission. And at the center of there is the Crab pulsar, which is rotating and throwing out this cloud of relativistic electrons and positrons. And that's what we see. It produces high energy electrons and positrons. But these aren't the cosmic rays because the cosmic rays are mainly protons. But that's one kind of. More common is this. So these are called shell supernova remnants. And this is what remains of 4 classic supernova explosions that occurred in these years. It's like letting a bomb off in the atmosphere. You're setting off release of energy in the interstellar medium, and it sends out a blast wave. Now, if you look at this one, Tycho, this is X-ray pictures of it, right? So this is hot gas, the yellow stuff in the middle that came out of the actual explosion. But outside, we see the actual blast wave, the blue, and what you're seeing there is energetic accelerated electrons emitting radiation, which is now coming to the X-rays. And we know from the characteristics of this radiation that there are very high energy particles coming from this blast wave here. And it's to do with the shock. This tells you that the acceleration is happening at a shock. Here you see a beautiful shock there forming around this protuberance here. And that's SN1006, that's closest you get to a spherical explosion. Cassiopeia A, which is actually the brightest radio source in the sky, seen here in the X-rays, all the stuff was thrown out through a very cloudy medium, and that messed up the explosion. So the shock wave is, quite structured and not non-spherical. But we know that they're producing the cosmic rays. Right, so we know from various means they are producing high energy particles. So if you look at in the radio emission requires GeV electrons. So that's mildly relativistic electrons. If you go to the X-ray, then you're talking TeV electrons. That's like the Large Hadron Collider. That's the Chandra X-ray telescope there. You have to get above the atmosphere to see the X-rays. But most exciting at the moment is the development of gamma ray telescopes. Right, and so 80 GeV is the energy of the gamma rays coming from there. And this is the telescope, recent development over the last few years, and there's a new telescope being built. And the way it works is like this. Right, so there's our supernova remnant. There's lots of protons being accelerated in there. And when those run into a cold proton, just a normal proton that's hanging around, it emits a gamma ray. Gamma rays, of course, go in straight lines, which is the beauty of them. So a gamma ray with about the energy of the cosmic ray heads off in our direction, encounters the atmosphere and breaks up in a shower. Then you have these optical telescopes on the ground which take a picture of the shower as it comes in, look at how bright it is and which direction it's coming from. They project it as a gamma ray map of this supernova remnant, which is quite a big one, so you can make a decent map of it. And you can see there's this kind of shell structure that goes with the explosion, with the blast wave. And so we can make a map of supernova remnants at energies of the protons must be hundreds of TeV, and we're actually seeing the particles that are in there that have been accelerated. Right, so there's good evidence that shocks accelerate particles, and there's loads of shocks in these radio galaxies. So how do they actually do it? Right, so here's our classic spherical blast wave, the supernova that happened in 1006. It's a blast wave expanding at 3,000 kilometers per second. And it's just like, here's a picture of a nuclear bomb going off. I think this is the original one done in 1945. And you can see the blast wave going on there. It's just essentially the same thing that's happening. And what happens is, so there's this shock around here expanding off into the surrounding medium at high velocity, and it's like a wall. And so a cosmic ray, a proton, gets, when the wall hits it, it gets bounced off ahead of it. So it's like this. Here's the shock coming along. It's like a table tennis racket, bounces the cosmic ray off in the future. It gets deflected and starts wandering around, and then the shock comes along, hits it again, and every time it gets hit, it gains energy. So the usual picture is like this. It's bouncing backwards and forwards between two of these rackets here, and if you keep on hitting it every time and there's no energy loss, then it gains energy every time it's hit. And that's the basic theory, and it seems to work. Right, so finally, move on to just a couple of slides about what we do in the laboratory, because it's really nice if we could reproduce this in the laboratory. So this is where we turn to the laser. This is a picture of an experiment done in at the laser facility at the Rutherford Appleton Laboratory on the Harwell site, if you know it. And this is the one time when I've actually led an experiment. It was a long time ago. I'm a theorist. Some idea of how we might do this. And so they gave me some time on the laser. And right, so the scale here is millimeters, not megaparsecs. And the time of which everything happens is nanoseconds. And in actual fact, you can't see it very well, but there's a kind of solid block here, and what you do is you shine your laser at a point on that solid block. It gets very hot, and so it expands away from the solid block in this direction, and as it expands it goes supersonic. So we've got a plasma supersonic wind tunnel here, and then you put something in the way of it, which was just a glass balloon, and then the wind hits it, and then it forms a shock going around there, which you can pick up by optical diagnostics. All this stuff down here is just the stuff that holds the obstacle in place. And it's like an aircraft going supersonically through the atmosphere. You get a shock wave that goes around it. And so we're producing shock waves. Right, so that's quite, with similar characteristics to the one you get in astrophysics. But things have progressed along a lot since then. That was 1988, a long time ago, and this is where it's got to now. Right, so this is a very large laser. In fact, it's the largest laser in the world. It's at the Lawrence Livermore Laboratory and its main purpose is to simulate the physics of nuclear weapons. But when they're not doing that, then they allow people such as my colleagues to get on it and do experiments with other things. Right, so that's the building that holds the laser. This is, when you look inside it, this is the actual laser itself. Now you might be able to see a human being in here somewhere. Yes, just there, I think. And that gives you some kind of picture of the scale of it. And what happens is the light gets amplified by passing up and down this hanger many times, getting an increase in energy every time it goes. This is a diagram of what it looks like. So here's the laser here. So that's in here. That's where the laser beam gets its energy. And then what you've got 192 laser beams, and you want to focus them down onto one spot, which is less than 1 millimeter across. So you have all these tubes which bring in the laser beams and into the target chamber. So you have a vacuum chamber, which that is it when it was being built. All these holes are where the laser goes in, and it all gets focused on something which is about 1 millimeter across at the center of that. So it's a remarkable way of getting lots of energy into a small region of space. This is an experiment that has been done just this year. Federica Fuser and colleagues are on that laser. And what they've done is, so these blue lines are the laser beams coming in, and they have a block of deuterated plastic here and here. And it's very much like that experiment we did in 1988. You hit a spot here, and then you get a plasma flow, supersonic plasma flow coming off it. But what they did was, they've got two of them, 25 millimeters across, and the flow meets in here, and therefore you get shocks in here. So this is the sort of gunge that happens, the interaction region between these two flows. There's a lot of activity going on there. And their results show that they get lots of energetic electrons out. So this is a spectrum. So that's the number of electrons against the energy, going up to 500 kilovolts, which isn't cosmic ray energy.
Sounds disappeared.
It's a lot hotter than just thermal energy, and it's producing the. Sorry, it sound's gone, is it? Can you hear me?
You're fine.
Right. Okay. This is my last but one slide. So if things keep on going, we're nearly there. But you can see these high energy electrons here, and they produce by this. So we're now actually getting. It's a bit early to call this the same thing as cosmic ray acceleration, but the same basic physics. And so we're beginning to get to the stage where we can actually do it in the laboratory, and therefore validate all these processes that we think are happening out there in the cosmos. Right, so here we are, final slide. Summary of it. There was Hess going up in 1912. And these are the places where we think the cosmic rays that have been formed, the very highest energy ones in things like these radio galaxies. And within our galaxy, not such high energy, but we know there's energy, energetic particles being here. And we've got beginning to have some theories, and the information on the flow of cosmic rays towards us and where they're coming from is beginning to build. And certainly we're pretty sure we know what's happening here. We know it's all close enough for us to actually analyze the physics properly. But in terms of the very highest energy ones, we're just on the edge of doing it. And I think we're about getting there. And at the same time, it's very helpful if we can do experiments in the lab, which validate it. So that brings me to the end of my talk. I don't know whether, well, I'll hand over back to George, and up to him now.
You need to stop sharing, Tony.
I need to stop sharing. I will try and stop sharing then. Right. I've stopped sharing. Okay, good.
Okay. Well, firstly, thanks very much, Tony. That was a fascinating talk. And of course, if people would like to ask questions, could you do it electronically? Because I've got, I think, 3 or 4 screens to go across. So if you just raise your hand electronically, that's under the reactions, I think. And then I'll see, oh, Chris.
Oh, it's Chris. Hello, Chris.
Hi, Tony. Yeah,
Fancy seeing you here.
indeed, indeed. Well, that was very nostalgic. You showing that shock picture from 1988 because I was involved in that experiment as well, as you may remember.
Yeah, I do remember. That's right. Yeah. Absolutely. Yeah.
The question I had was this: you talked about Cygnus A, and you showed the picture of it as probably 2 colliding galaxies. Does the fact that there's actually only 2 jets coming from that imply that there is actually only 1 active black hole in that complex, and they probably haven't collided yet?
I think I'm sure you're right. Yeah. Yes. I'm not sure anybody really knows what's happened, but I think the black holes probably interacted a while ago, and now we're seeing all the stuff. Maybe merged. There might only be 1 there now. And now stuff is falling into that enlarged black hole, which is left over from the merging of 2 other black holes.
Yeah, if there were 2 black holes before, would there not be evidence of additional jets sort of in the outside regions? Where, I mean, now there's only 2 jets, but you'd think there might be the relics of more jets if that was the case.
Well, that's an interesting supposition. I mean, I would guess that, well, I'd guess a number of things. Firstly, that, right, it's a matter of timescales, that jets might have dissipated by now. The other thing is that I think you'll only get well-ordered jets if you've got a stable system. If things are really sort of messed up, then you're not going to have a neat system where everything comes out in one direction. I mean, it comes out along the rotation axis, and so you've got to have a clear run for things to get away from the black holes, and the rotation axis has to carry on in the same direction. But I must admit, I'm not really an expert on that side of things. So I think I'm right, but I'm not necessarily right. But the thing that occurs to me while you say that is, why don't we see any with 2 jets? And I'm not aware of any that have 2 jets. So that's an interesting thought, that.
Okay, thanks.
Okay, do we have anyone else? Oops, hang on, I think I saw a hand go up. Steve.
Yeah, I don't know where I missed something as you were going through. I was trying to digest everything as it was coming through. But I seem to have missed the point where the energy goes from a reservoir at the end of each jet to particles that are traveling at almost the speed of light. At what point do they actually reach that speed and come to us?
A long time ago, right? So, so if it ever looked like this really energetic jet in Cygnus A, then the acceleration would have happened at that time. And but it's not just a matter of when you accelerate them, it's how they get out. Right. So I don't know whether you're familiar with tokamaks, magnetic confinement for doing fusion and things like that, where you try and hold the particles in while you do get all the fusion energy out. So maybe those, well, they seem to be a little bit like giant tokamak plasmas, and it takes a while for the particles to get out. So the guess would be that there's some of them escape quite quickly. But when you do all the calculations of how quickly they should be able to escape from something that size, you find that it can take them many mega years to actually get out. So they can be leaking out now, but accelerated a long, long time ago. So that's what we think is happening.
Do they reach their speed as they leave the poles of the black hole? That's what I meant, or is it some point a bit later?
Right. So what we think, we don't think it's happening close to the black hole itself. Now, there are some particles accelerated there, because we know that because we've seen some energetic neutrinos coming directly out of black holes along the jets. So we know there's strong particle acceleration happening at the black hole itself, at the base of the jet. But if you want to get to these very high energies, the black hole area is too small, and you need something much, much larger. And so the key to it, so if you think of what happens when you've got a charged particle in a magnetic field, it tends to go around in a circle, right? Spirals around magnetic field lines, because it's always being continually deflected by the magnetic field and its charge. It's like a current. And the size of that circle, as it goes round and round, gets bigger as you go to higher energies. And you can't accelerate something in a structure which that circle is bigger than the size of the structure, right? So that places a limit which says whatever produces these very highest energy particles has to be very large indeed. And that's why one looks at the very largest structures that we know of in the universe. So we know you can get to lower energies close to the black hole, but what you've got to do is keep them in this very large structure as they go round and round, and find some way of giving them a kick. And that's what the shock does. If you've got shocks in there, they come along and give it a kick every time a shock goes past. And we think that's what's happening. But the whole thing is spread over multiple kiloparsecs. You can't do it in a small distance, and the black hole is a small distance.
Oh, it's like a resonance thing, like these giant guns that they were trying to build, where you have extra explosions along the barrel to give it an extra boost to get the speed.
That sounds like a good analogy.
Right, thank you very much.
Yeah, good, thank you.
Okay. I'm trying to whiz through the screens and see if there are any hands showing. Tony, are we clear what mechanism is forming these, what I'll call ultra-fine jets?
That's an excellent question. And there are some very good theories, and they always certainly work, but because you can't, it's very difficult to get observational data on that process. It's very difficult to validate them. But it comes down to magnetic field again. Right, so if they're going to come out, so as stuff falls into a black hole, it releases a lot of energy. So that energy is going to come out, and so there's no mystery about where the energy comes from. The question is, why does it produce these magnificent narrow jets? And what they think, what it is thought, is that a black hole actually has an electrical conductivity. And as it rotates, as is known from a conductor, it drags magnetic field with it, right? So you think of these magnetic field lines, right? So it's rotating like that, and these magnetic field lines are sticking up, and it's rotating. So it winds the magnetic field rounds into a kind of spiral, and that acts like something like an elastic band, separate sort of, and it holds in the flow trying to get out of the black hole, and so it comes out along the axis with these magnetic field lines holding it in as it comes out. And that's all, in some form or another, that must be what is happening. There can't be any doubt about it. But how you actually get those very fine jets is so totally extraordinary, really.
Yeah, certainly enormous amount of energy in a very small sort of volume of space. Malcolm, a
Oh,
question.
yes, thank you. I just wondered what the positional accuracy was of the Auger telescope. I mean, you were saying you got your points well distributed across the sky. But I was wondering how well you could tie those points to particular other sources to look for, are they all radio galaxies?
Right. Okay. So, so you can actually tell the direction at which the cosmic ray arrives at the Earth very accurately. The big problem is whether it got deflected on the way here. So everything's to do with magnetic field. So the magnetic field between us and these other galaxies is about 10 to the minus 9 Gauss, which is not much, right? Very tiny. The Earth's magnetic field is a Gauss, so we're talking about a billion times smaller. And these energetic cosmic rays plow their way across this magnetic field, but that magnetic field is just such that it can start making them deflect in the direction they're going. And so by the time they get to us, they've been deflected by a few degrees, maybe 10 or 20 degrees. And so you can't just simply...
So that randomizes the distribution to some extent.
Yeah, that's right. Yeah. So I mean, it's something we're looking into. James and I are still working on this. There's trying to figure out how to match back the different amounts of deflection of magnetic fields to what we're actually seeing on the sky. Because most of the particles seem to come from all over the place. Most of them don't come from any point at all. So there's quite a mystery there, which we're trying to figure out. And it has been quite a bit of a disappointment. The idea was you turn this Auger telescope on and you see the particles coming from a certain direction. You keep it on for a few years and then you know exactly where they're all coming from. But it hasn't turned out to be like that. And there's obviously something going on that hasn't been fully understood yet.
Okay, thank you.
Okay. Oh, Chris.
Another question, based on what you were just saying about the two telescopes, there must be some region of the sky which they can both see, is that right? In which case, is there agreement between the observations,
Yes.
the telescope array and the Auger array?
Ah, you're asking some, right. You're asking some good questions, Chris. The answer is
question, not an astrophysics question.
No, this is real astronomy, not astrophysics. Yeah, there seems to be about a 20, I think it's 20%, I can't remember exactly what it is, difference in their energy scales. And how do you measure an energy of one of these? I mean, it's a very difficult thing to do. So I suppose it's not really surprising. So they have these arguments about who is more accurate than the other. But to be honest, I think it's pretty amazing that the scales come in to be
actually, what I was getting at was really the spatial distribution or the angular distribution of sources within the region that both telescopes can see. And is there agreement between the two of them in that?
There is a difference, and this is really interesting, right? Because and what you can do is, once again, extraordinarily difficult from an observational point of view. You can get some idea of whether it's protons that are coming through or whether it's ion nuclei or whatever. And there seems to be a different composition in the northern hemisphere than in the southern hemisphere.
Wow.
But that's not necessarily that's surprising, because as well as being in a galaxy, we're also in a cluster and a super galaxy and things like that. And so there is structure in the universe out to those kind of scales, and so you're looking at a bit of a different environment. But the other thing is, this is what we're working on, is that there's the possibility that some of these are actually coming as reflections of clouds rather than direct from the source. And if that's happening, then you might expect to get different compositions, because different particles will reflect differently and go different distances. So it might be, I mean, you know, if you ask a really serious observer on this kind of thing, as I have done, you know, because being a theorist, I don't know what to make of this kind of thing. And he says, don't believe anything. That was what he said to me quietly. Now it's on YouTube, but at least I haven't put a name to it. So, because this business, and the amazing thing is what can be done observationally. I mean, I'm a theorist and I can build my theories, and that's relatively easy. But to make these observations is truly amazing. And it's really at the limits. And so if you go to the big conferences on cosmic rays, all the argument is about instrumentation and things like that, and how you interpret showers coming in through the atmosphere and that kind of thing. But, yeah, but the thing is, we're making progress. You know, that we know things now that we didn't know 10 or 20 years ago. And if they can progress the technology a bit further, and then we'll know a bit more. And it's just about getting to the stage with these highest energy ones where people like myself can come in and start building theories which have some connection with reality.
Yeah, great. Oh, thanks very much.
Thank you, Chris.
Okay, do we have any other questions? I'm going to try and flick through the screen to see if there are any hands up. Okay, I think the answer is you've clearly explained what's going on and answered the big questions. So once again, can I ask us to thank Professor Tony Bell for giving a fascinating talk in a really unusual and very high energy arena. So thanks very much.
Well, thank you. I just wish I could see you all. I mean, I know I can see you, but it's not the same thing. And so, yeah, but anyway, it's been a pleasure for me as well.
I suppose
Thank
it's
you.
better than not having the talk at all, which would be a really bad alternative.
Well, I always look around at people's faces and see what they're responding to, and it's difficult to do it under these circumstances. But there we are. It's been a pleasure for me. Thank you.
Obviously, Tony, you're more than welcome to stay on if you wish, but please don't feel obligated to do that.
You're not all going through a cup of coffee, are you?
I think we are. We're gonna have a small break. Where are we at now? It's about 20 to 9. So if we can get back together again at about 9 o'clock, and that'll give you a chance to grab a coffee and have a comfort break. We've got 3 speakers afterwards, obviously our own members, David, myself, and Steve Harris. So if anyone else wants to have 5 or 10 minutes, please let me know. We can do it via the messaging system on here. I'll leave the thing running so you can talk to each other to your heart's content, but I'll stop the recording. So if you want to ask Tony, you know, who was the guy who did the embarrassment, then okay. Answer to your question, Trevor, yes. You want to show that now before the break, or would you do it afterwards?
You can do it now if you like. If I wasn't sure when Tony was going to disappear, but I think you may have said that the jet coming out of M87 was only visible in radio, or maybe you said mostly visible in radio. But I managed to take a picture of it in April, just during the start of shutdown. So I just, in case anybody wants to squint their eyes and see whether they can see it. I don't know if you can see that.
Yep.
Yeah.
I'm not sure how well that's going to come through, but if you look very carefully at the center of M87, you'll see coming down and to the right about 45 degrees or so, you can actually see the jet. if you can't see it through Zoom, I'll send you a Flickr link and you can go and look at it on Flickr, on my Flickr account.
Could you move your little cursor towards it?
Yeah.
So it's about there.
Yeah.
Can you actually go to full screen so that we can see it a little bit bigger?
Yeah, let me see if I can do that. Everything's hidden now behind the Zoom controls, so let's try that. Is that any better?
Yeah, it's there.
So it's about there somewhere.
Yeah.
But it's quite small.
Yeah, I can see it.
It is small. I'm not. I hope I haven't underwhelmed you, but just to prove that it actually is visible with a regular telescope.
That's better like that.
Yeah, I think whatever I said, what I meant to say was, I mean, it can be seen because it's seen in optical because the Hubble telescope sees it. But when I had this discussion before with another astronomical society, they told me that they couldn't really pick out the jet issues of relative brightness and resolution and things like that. And so, but they said they could just about see it. And what you're showing, I think, probably fits in with what they were telling me could be done. But you're obviously seeing the center of the galaxy quite nicely as well. So you obviously got good technology there.
Yeah, it's not
brilliant.
too bad. Anyway, just since you mentioned the jet in M87, it just made me think, and that was taken in,
Can I ask
in April.
this, have you got a new?
I think the audio went then. I didn't hear your question, Tony.
I've lost the image as well.
Oh.
I think he's dropped out.
Yeah.
Is he gone?
Well,
Seems that way.
I think so, yeah.
Have you tried taking off the brightness of the galaxy, the profile of the galaxy, and then so you subtract it, then you just see the jet without the broad light of the galaxy?
Patrick, you want
haven't.
to say something?
No, I was just saying goodbye.
Oh.
Nice talk. Thank you.
Anyway, I'm sure you're all hear the kettle beckoning or the wine bottle, so I'll stop sharing.
But thanks for showing it, because it just shows how good imaging has become. Okay.
Okay.
Well, I'll say goodbye now and enjoy your cups of coffee, and I think I'll go and.
Yeah.
Is it going to full screen? Okay. You got full screen now? Is the sound
that's fine, David.
Okay, sound level okay?
Yeah.
Okay. It's about helping Hubble, or how can amateurs be of some use? Let me just try and move the images out the road. Yeah, that's better. Okay. This is a story about this object with a very complicated name. It was an unknown variable star which suddenly brightened in July last year. The TCP is the Transient Confirmation Page. That's the IAU Central Bureau, which people are supposed to report objects that suddenly and unexpectedly brighten. This was a Japanese guy caught this and reported it. The rest of the long name is just the RE and DEC coordinates. So this is a light curve from the AAVSO, the Variable Star Observers in the US. Along the bottom, you've got a timeline from July last year when it went off right up to the present time. And this is the brightness of the object, the magnitude. It was picked up around 8th magnitude, very rapidly came down. Then it started doing unusual things. It, instead of just dropping off and fading away, it had a couple of short blips. Then another fairly major, but not as large as the first outburst. Then another little blip. Then it started to fade. Then it had another outburst, an even bigger one than the previous one. and then it faded. And then in March, the end of March last year, it had another one. Now this is pretty unusual behavior. And since then, it's been fading gradually. The blue dots are measurements I've made and submitted, and a lot of other amateurs have been contributing to it as well. But what's interesting is down here, as it's fading away, the range of measurements is getting larger and larger. And you'll notice that most of mine are around the bottom, down the bottom here, but there are people that are reporting it almost a whole magnitude brighter, and that was starting to become a problem, so we'll see in a minute. So that's the field of view. This is an image I took a few days ago before the rains came. The object in question is that rather inconspicuous looking star now because it's down about 15th magnitude. When it first went off, it was about the same brightness as one of these stars. It was very conspicuous. But the problem that's causing that uncertainty in the reported brightness of the star is this little star nearby. If you've got a short focal length telescope, you're probably not resolving these separately. And rather than just picking up the gradually fading magnitude of the variable, you're picking up a much more constant magnitude, which is the sum of these two. And that was starting to become a problem over the last few months. Now, what is this object? Well, our best guess is that it's a fairly standard, apparently cataclysmic variable, or dwarf nova, as they're sometimes called. It's a binary system. This is a fairly regular main sequence star, a bit like the Sun. This is a white dwarf, which is the very hot remnants of a star which has evolved right through its life cycle. It's become a red giant, shed its outer layers, and what you're seeing is basically the white hot core of a star, which is mainly made of carbon and oxygen. And material is transferring all the time from this star towards the white dwarf. But because the two stars are orbiting about a common center of gravity somewhere in the middle, by the time the stuff leaving the star gets over towards the white dwarf has moved a bit further around in its orbit. So it misses it and it starts to go into orbit. And gradually what happens is you build up a disk of material in orbit around the white dwarf. And that can go on for decades, for centuries. The stars, we've no idea how long that's been happening on this star. But what eventually happens is that the disk gets fuller and fuller. It starts to get more and more viscous, and eventually it heats up and becomes tremendously hot. And it's that very hot disk which causes the peak of the outburst. And gradually the material in the disk falls back into the white dwarf. The disk cools down and the thing fades and gradually becomes less visible. What they think has happened in this particular case is that the disk hasn't properly emptied. It's partially emptied, but it's started to build up again, and that's led to a succession of short rebrightenings and then longer outbursts of the system. That is very unusual behavior. I mean, there are stars which have been seen to do one or two short brightenings after a major outburst, but not the whole sequence that we've been seeing on this star. So the result is that the professional astronomers started to get really interested in this star. Some of you may know of a professor at Warwick called Warwick Gansika. He has really been pulling a team of observers together, working with somebody in Finland called Vitaly Nustraev. And they've been encouraging amateurs to keep following this thing. So there's quite a large team of amateur and professional astronomers now gathering data about this object. They got approval to observe it with the Hubble Space Telescope back in April, on April the 10th. That was the scheduled date. They were using something called the Cosmic Origins Spectrograph, COS, which observes in the UV, because the white dwarf, the main emission from the white dwarf is in the ultraviolet. It's just very hot. These things are many tens of thousands of degrees Kelvin. So this was all planned. This would only go ahead if the star remained faint, because if it was to go into one of these outbursts again, it would potentially damage the detector and the instrument. So they're very careful about being sure that this object isn't bright before they observe it. Unfortunately, as I mentioned earlier, on the 31st of March, the last of these bright outbursts happened, and the whole thing was cancelled because you can't basically take the risk of doing it. What actually happens with these objects is quite interesting. They scheduled another attempt on September the 12th. So leading up to this, they have to they upload instructions to the telescope, but they give it 2 coordinates for the target. One is a region of blank sky close to the target, and the other is the real target that you want to observe. And the default instruction in the first set of instructions uploaded is to observe the region of blank sky, just because that's the fail-safe situation. If all else fails and the object happens to go off at the last minute, you can still observe blank sky and protect the instrument. If only if the target is reported still faint immediately before the scheduled observation, what they do is they uplink a single instruction, a single command, which switches the coordinates of the target, so it then actually observes the thing they want to observe. If they don't get that instruction, they'll observe, they'll get a very expensive spectrum of blank sky. So the observations were scheduled to start at 7:16 on the 12th of September. Boris got a message and he sent it round everybody involved to say, we need to have the latest measurements of the brightness of the system by 1300 hours on Friday, September the 11th, the day before. That's so they can send them to STSCI, persuade them that the thing hasn't got bright, and they can continue and take the spectra they want with the object. This meant that the last opportunity to observe the star was still going to be fair, would be on the night of Thursday, this September the 10th. That's the last dark sky that would allow anyone to get a measurement before midday on Friday. Now, the problem that the professionals have become very aware of was this uncertainty I mentioned earlier about observing the star, and it was clear that some of the people who were observing it were measuring measuring the 2 stars blended together, and they weren't necessarily giving a very accurate value. So what they've been doing is that a few of us who seem to be producing more reliable, fainter measurements, they actually asked us to send the raw images that we had taken. They did this a couple of weeks before we were getting to the deadline. Said, send these raw images. I want to confirm that you're actually measuring what you say you're measuring. And they measured our own images ourselves. And as a result of that, they came up with 4, what they called trusted observers in this team that we were asked to try and help at the final end. A chap called Tamás Tordai in Hungary, Arto Oksanen in Finland, me here in the UK, and George Schoberg in New Mexico. And these are in increasing order of westward longitude. So that gave them a chance. At least one of the 4 of us was going to be able to pick it up that night before. And probably George would be the one who would most likely catch it last because he's much further west. I'd probably get it after Arto, and Tamás would be the first one to pick it up that night. As it happened, George was unable to observe that night. I think it was a combination of cloud plus smoke from California, which was just drifting eastwards across the US. And he was basically out of action. So looked like I was going to be the last person to be able to send him an observation. I measured it at 15.81 in magnitude. That's a V measurement with a V filter, just before midnight on September the 10th. And that was reported back and was the last measurement I was able to make. I did have another clear night the following night and continued to pick it up at 15.82. So even on the Friday night, it was still faint. The conclusion was that they then went ahead. The HST observations were made on the 12th of September. This is a spectra, one of the spectra they got back. It's very weird. It's not like most spectra I've seen, but deep in the UV. The black line is just the real spectrum. The red line is an attempted, very initial attempted fit by Boris Gansica to try and understand what the nature of this object is. And you can see it's broadly at the right sort of shape, but there are major departures here. There's a bump here, he doesn't know what that is. There's a bump here, he doesn't know what that is. This is a Lyman alpha, line, which was expected, but they're very deep absorption bands. So they've got a lot of data here. The final twist of the story from their point of view was they scheduled 6 COS exposure or integrations to get spectra. 2 of these didn't happen because the HST took too long to acquire its guide stars. The HST is getting fairly old and decrepit these days, and it does struggle to point reliably. So if any of you are having struggle getting a fix on a guide star in your back garden, just spare a thought for HST. It still has very similar problems to what you do in catching, following its guide stars. There's got to be a tremendous amount of analysis and probably some more observations to come on this. And eventually in 2 or 3 years, I imagine we'll all find out what the nature of this object really is. It's clearly something rather unusual and verging on unique as far as previous observations are concerned. So I thought it was interesting. This was just one example where if you're in the right place at the right time, you can take observations which are really very helpful. At this point, I think virtually all the professional observatories were being locked down because of the virus. So it was going to be very difficult to get professional observations around this time. And it was amateurs that helped them out in the end. So, end of story. Thank you.
Thank you, David. Do we have any questions for David?
Yeah, I got one, George.
Yep.
Go for it, Paul.
Hi, Pauline.
Hi, David. Can you explain to me the technology, though I probably won't understand the answer, of how you can get so precise magnitude measurements, 15.81, you know?
Yeah, well, you take an image of the field. Well, in fact, you take a whole series of images of the field. There is a catalogue that allows you to get the magnitudes of a number of stars in any field in the sky. It's called APAS. It's something that AABSO has done, the Amateur All-Sky Photometric Survey. It means that in any image that you take, there'll be stars with known magnitudes. So you've got a reference point against which you can measure the magnitude of any star in your image, and that's basically how you do it. And I compared it with 5 stars with known magnitudes and was able to get a really fairly tight measurement of the magnitude. The uncertainty on that is probably about a couple of hundredths of a magnitude. So
fantastic. Thanks, David.
Yeah.
Okay, any other questions for David? I'm flitting between the screens. No.
Stunned silence. Good.
Thanks very much, David.
Okay.
John, are you able to go next?
Can do, yeah. Yes.
Okay, go for it.
Okay, well, as you know, I usually taking images of deep sky objects, but just recently I've gone planetary because Mars is coming up to opposition. Really wanted to have a good go at it, so I've converted the telescope into a planetary telescope. In other words, in a deep sky, you're trying to shorten the focal length to get the wide field, but for planets, of course, you want to get as long a focal length as possible to get small fields. I've got loads and loads of data, which I've only just started to process because you just grab all the data when you can, when the weather enables it. And then it all sits on the computer. And I've got hundreds of gigabytes of data because I'll explain how I've been doing it. Let me see if I can bring up a picture. I can share screen. Yeah, you see that?
Yeah.
Now, what I've got here is a C14 14-inch Celestron, and I've got a 2.5 times PowerMate Barlow, which makes focal length, the focal ratio 27.5. So it's rather long focal length, but it's on an EQ Skywatcher EQ8 mount, which I must say is coping admirably. It's locked onto the planet, and I'm not having to tweak it hardly at all. Dead impressed. It's fantastic. Anyway, I also invested in a new camera. It's the new ASI 174 no camera. It's extremely fast, is why I've got so many gigabytes of data. Last time I was out there, I was actually doing 250 frames per second. Now, back in the days when I did some planetary imaging several years ago, you were pushing it if you were getting 60 frames per second. You really were pushing it. But this camera is very sensitive and very fast, and it's fantastic. So you just take loads and loads of AVIs and you just select the best ones. Software does that, of course. Software is very, very clever these days. But this one was last Wednesday. Now, it was a bit like tonight. It was actually tipping down with rain. So I thought, okay, rainy tonight. So I settled down in front of the television, and I sort of got past midnight and I noticed the moon was shining through the window. I thought, oh, hello, what's going on here? So I looked out and it was really, really clear. You could see a few clouds coming over. So I checked the radar and see you've got at least 30 minutes. So everything was soaking wet. It was cold. I was warm because I'd been sitting by the telly. So it was a toss-up whether I watch another episode of Star Galactica, go out in the observatory. Luckily, I decided to go out in the observatory because actually for 30 minutes, it was some of the best seeing I've so far, which is quite strange because the jet stream was raging overhead at the time. But you can never tell. You have to just keep trying. So I grabbed all these AVIs. This is an RGB image, the red filter, green filter, blue filter. About 20,000 frames per channel. You end up processing about 10–15% of those. So if you can grab as many frames as you can, you're bound to find some really good ones in there. And anyway, I processed it and I'm really, really pleased with the result. And as I say, this is only the first one I've done. I've got loads to do. Certus Major is sitting on the meridian now. I particularly wanted to get that object, and I'm really, really pleased. I've not really looked yet to see what detail you can see. It's a job to find a decent map to actually find all these features that you can pick up on here. So really, really a good start, I thought. So also been doing some infrared. This is infrared filter, and it seems to work really, really well. With infrared, you can do longer exposures. With RGB, you have to watch the rotation of the planet. For too long, rotation of the planet will blur the detail. But of course, with just one filter, the infrared, you can do a nice long one, and I'm talking about 30–40,000 frames, which is gigabytes. So anyway, I'm really pleased with the infrared. I'm not sure why the infrared is working so well. It obviously gets through the turbulent atmosphere much better, and it really is quite impressive what you can do. But one more to show, which I literally did this evening before I came online. Another one the same night, RGB. It's actually staggering what you can do with these new cameras. It wasn't that expensive, the camera. Anyone's thinking of getting into planetary imaging, I would certainly thoroughly recommend the camera. I did need to upgrade the laptop because, of course, you need a lot of space to store all the bits, and also USB 3. So I treated myself to a really, really fast laptop, and so far it's really paid off. So I'm really enjoying myself with the old planetary work. So I haven't done any for years, and Mars is coming up to opposition in about 10 days' time. So I hope it stops raining soon. Get out there. So anyway, that's what I wanted to show tonight. I hope I'm going to have lots more to show sometime in the future. But if I can stop share, there's just one more thing I'd like to show you. Treated myself to either a very late birthday present or a very early Christmas present. And I really don't understand how it works, but can you see
that from, John?
Can you explain how that's working? Apparently, it works if you shine a light on it.
What is it?
Well, it's the globe of Mars. So you can
Oh,
get a
yeah,
bit closer.
And it's
Apparently,
rotating.
it works by the Earth's magnetic field lines and light. And I don't
Magic.
understand.
Mm,
The faster it goes.
Well, I think I know what you've been photographing.
No. I mean, it's
Some
amazing.
fake Astropics.
I've seen them ages ago. And I thought, yeah, I'll get one of those. Rather expensive, so.
What's
There you
it
go.
mounted on? Is it got some kind of stand, or are you turning it round with your hand?
No, no, it just rotates. It's in a glass perspex ball.
Oh, I see. It's inside something.
It's floating
okay.
inside a ball.
There's a ball inside a glass, a perspex cover.
Yeah.
Okay.
You put it a bit further away from the camera so we can see it.
It's got a mouse inside on the
Should start rotating in a minute.
Where did you get it from? What did you say?
I've got it online somewhere. I can't remember. I could find the link for you if you want.
Amazon.
Napster's gone to sleep, I think.
Yeah, stop rotating.
169.95 on Amazon.
Yeah, that's going now.
does it rotate in 24 hours, 39 minutes and 40 seconds?
Yeah.
Did you use Amazon Smile, John? And did you remember to donate to Newbury?
Sorry, I forgot.
Oh, whoa, 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 whoa.
I wish somebody could explain how it actually works.
Well, you click on Amazon Smart
Magic.
and you get a penny.
Google it, John.
Yeah. Okay, folks, that's me.
Okay.
Very good.
Anyone got any sensible questions for John? Apart from the odd comment, which is some of those images look absolutely brilliant, and some of the small features are not that big.
By the way, I've been using, I don't know if any of you guys, anyone in this new Nick Simonik on it in this month's Astronomy Now. It's called Sharpen Artificial Intelligence or something, Sharpened AI. And it's absolutely brilliant. It really is got a lot of potential. You get it for 30-day free trial, and Mark Harmon's been using it on some of his sky objects, and it's absolutely staggering what it does. It's well worth looking at. Well worth looking at. And I've just tried it on the planet. I used it on that last image of Mars. Absolutely staggering.
John.
I recommend you have a look at it.
John, fantastic images. How are you focusing? Are you using a motorized focuser or are you focusing manually?
Yeah, definitely you need electric focuser.
Okay.
Also a big bonus, I also invested in a electric filter wheel. That does make life so much easier. Because then you don't need to touch the telescope at all, you see.
And are you using mind you, you're monochrome, so you're not using a dispersion compensator then? You're doing it.
I have tried one. I've had one for ages, and I've also got a color camera. So I tried it one night, and tell you what, they are magic. Those ADC, absolutely magic. It's wonderful. I'm going to try do some more with it. Worth having those.
Yeah, I agree. You need those with the color camera. You don't need them with monochrome, particularly.
Yeah.
And I also agree.
I was quite impressed with the difference it made with the color camera.
Yeah, the ASI 174 is an excellent camera. I've got one of those as well. It's,
yeah.
Yeah, grease lightning doesn't begin to describe it.
Yeah.
Okay. If that's it, then I think I'll see if I can share the screen. And you may have left the course, but I'm still keeping it. Sorry, this is an image I took a couple of years ago of M87, and as you can see, the jet is there. Just really to make the point that Trevor was making, that amateurs can take images of the jet. Anyway, this is.
You mean Tony, George?
Oh, sorry. Yeah. I'm seeing so many names. I'm becoming name blind. Right. So this is images like what I took in September. That's my dome, and yes, that is horse protection. My neighbour leaves a horse there. I woke up this morning, and I don't know if it's happening on your screens, but there's a big block of dead pixels there. I don't know if you're seeing them or not.
No.
No.
Nope.
No, well, it's just my screen. I'll carry on then. Anyway,
All looks good.
That's the dome. That's the telescope that I use for all these images, bar one, which is a Takahashi FSQ on a 10 micron mount. And at the back end here, I've got a manual rotator, so I can orientate the image so it's consistent if I'm taking it over multiple nights. That's the camera that I use, which is the ASI 1600, which is a mono camera. And there's the filter wheel. And I just need a couple of extension pieces, and that's the manual rotator. So that's the equipment that I use to show that I do occasionally take non-deep sky objects. Here's a picture I took of the solar eclipse that I went over to the States with. And there is just here quite a nice prominence that was visible. Anyway, back to deep sky objects. These are ones that I've taken. This is M97. It's about 2,000 light years away, and it's about 8,000 years old. What I quite like with it is, I think there are 3 shells, and certainly you can see there are 2 there. And of course, there are these smaller, fainter galaxies, which is why I've left the background slightly grayish, because it helps show up those faint galaxies. That in total is a 5-hour image. So there is something like 2 hours mono and then 1 hour red, green and blue, making up the 5 hours. The next one, this is M108, which is a barred spiral galaxy about 14 megaparsecs away. It's got an absolutely enormous black hole in the middle, which has 24 million solar masses. And it has huge hydrogen clouds that extend out for several kiloparsecs out from the galaxy itself. I think they're spotted with radio. This was a 4-hour image made up of 5-minute exposures, which I do unguided, and then I take 12 of those under a particular filter, and that makes up the red, the green, the blue, and the mono. I will try and look to see if I can get 2 hours with them. This is one that I've taken just a couple of weeks ago. This is the North American Nebula. And if you look at it, you can see why it's called the North American Nebula. It's a mission nebula. The actual size of it is huge. It's about 10 times the size of the full moon. This field of view is about 3 degrees by 2 degrees. And I think it was Jerry at Reading highlighted to me, is this part here is something called the Cygnus Wall, which is an enormous region of star formation. So just zooming in on this and slightly processing it differently, you can start to see not only the dark clouds up here, but the Cygnus Wall down here, and there is intense star formation going on in there. It's about, well, the odd thing is there were 2 or 3 different estimates about how far away it was, 1,500 to 3,000 light years away, but we seem to be settling on 2,000 now. And why there were differences in the measurement is a little unclear. Okay, and the last one that I took probably about a week and a bit ago is the Elephant Trunk Nebula. This is a hydrogen alpha image. And this is the Elephant Trunk Nebula as it's called. But you can see there's a huge amount of detail in this image, which I've turned sideways to sort of show off the elephant trunk. It's an odd object in that it's got the whole thing's been lit up by the bright star, which is giving off a lot of UV, and at the same time that's generating a lot of pressure in the hydrogen gas clouds, and there is star formation going on. So some of the material is pretty heavily compressed, and that compression causes protostars to be formed. So there's an enormous amount going on there. And if we just zoom in a bit to the Elephant Trunk Nebula, that's it sort of zoomed in. And if I go back, what you can see there is it's just a huge part of the sky, and the only drop off where there's very little gas is really round here and round there as well. But most of the field of view is just full of glowing hydrogen, and that's quite a spectacular looking object. And basically, that's it. So that's how I kept myself busy in September.
Thanks, George. Very good.
Very good.
Thank you.
George, were they H alpha, did you say?
Sorry?
Were they H alpha, those last ones of the elephant's trunk?
What, the last one?
Hydrogen alpha?
Yeah.
Just hydrogen alpha?
Yeah, it's, I'm trying to, hang on a sec, just let someone in. I think I used the 7 nanometer filter.
All right.
I bought a 12 and then went for the 7. Well, actually, somebody was selling a set of them, and they were the Barda ones, and they were reasonably narrow. So I've got the H alpha S2, which seems to be not the most useful filter I've ever had, because a lot of times I'll do an hour's worth of exposure and nothing really comes through. So looking at doing more bicolor narrowband HA and O3.
Okay, thanks.
Okay, if no other questions or comments, it's Steve's turn.
Yeah, I think mine's a little bit at the lower end of astronomy. It's, just to try to encourage people to do something that I've been meaning to do for the last 12 years and just finally got around to doing it.
Go on, you've intrigued us.
I hope Steve is going to keep it clean.
Not Saturn.
I think you might be muted, Steve.
Don't complain.
Can't hear you, Steve.
Do it. Right. Right. So, slideshow. Right, can everybody see that?
Yep.
Yep.
Right.
Yeah.
So I suspect everybody already knows, but when you look up into the night sky, we can see that Jupiter and Saturn are fairly close together in the sky. And for anybody who's a beginner and joined our meeting, what we actually call this is a conjunction. So when two or more objects are together in the sky, we call this a conjunction, and they've come together. If for a wider conjunction, you can see in this picture of the night sky, or a chart of the night sky, we've actually got 5 stars together across the southern sky, 4 of which you can see on here with Jupiter. We're coming from the west towards the east. We've got Jupiter, Saturn, Neptune, Mars, and Uranus is a little bit further along, with Venus and Mercury not actually joining this conjunction. But I just wanted to talk about the conjunction of the 2 planets, Saturn and Jupiter, because they're going to do something quite interesting over the rest of the year. So what's actually happened on that is that as the planets move around their orbits, they obviously catch up and overtake each other. So on the 14th of July, Jupiter was in this position where Earth was coming around and undertook Jupiter at midnight. Well, we say midnight, but not quite midnight, but at midnight of the evening of the 14th of July. But it didn't really make much difference because it didn't look any different to the night before, the night after, or whatever. So that was quite, it was interesting to actually look at it on that night to know that it was actually at opposition. And a little bit later, I think it was, I can't remember the date now, but a couple of weeks later, Saturn was in the same position. So Saturn, when it was in this position, Earth had come round and it was in line with Saturn, Earth, and the Sun all in a straight line. So we were overtaking at this opposition position in the sky. So just looking at the planets, this is a picture from Starry Night, just to show what it actually looked like in my garden. And I'll show you another picture in a minute. So they do actually look close in the sky, which is unusual. But they are going to get close. There's that picture that I took with my DSLR from my garden. And you can just see the trees, which is quite similar to that other picture with Jupiter and Saturn together in the sky. But what's actually going to happen is that the 2 planets are going along the ecliptic. As they go along the ecliptic towards the rest of the year, they will actually be getting closer together. So on the 21st of December, they will be in the sunset and in the bright sky, but that's when they come to the most interesting position. So with the 2 orbits, the red orbit here is Jupiter, and the brown one is Saturn. And you can see that they're converging together, and just over here, they appear as one object with 2 names. If we zoom in on that with a telescope, what we actually see is the 2 planets in the same field of view in most reasonable telescopes that we use ourselves in our gardens. They're in fact going to be 0.1 of a degree apart, which is 1/5 of the diameter of the moon. So they're going to be pretty close together in the sky, and they'll be visible in a telescope, and we should be able to see the moons and everything else with the 2 planets close together. So just going on for a little tangent, when Comet F3 was around, I used my DSLR, which I bought for myself when I retired in 2008, with the dual purpose of using it for general photography and doing some astrophotography. And I took this picture from Greenham Common around about midnight on a clear night, and I stood the telescope on its normal tripod, pointed it, took some pictures, I had my telephoto lens on, but the camera's also got a sort of a Barlow facility on there where I can magnify the image by pressing a button by 1.4 and 2 times. And this was a picture that I tried to take with that. The trouble was, as the star was moving, I had little control over the tripod that I had to unclamp, move to follow it along. I missed it and I couldn't find it again. So I thought, I've got something to learn from here. What I need to do is to get something that I can put by the side of the camera and see where the camera is pointing on a dark night, because the little screen on the camera doesn't really help very much. So what I did was made this little platform to fit on my Altaz tripod, which I normally use with my PST, which is redundant at the moment. So what I did was put a camera mount, which I had in the junk drawer, and bolted that onto one side, fitted a finder on the other side with a shoe, and the two operate together. So just to try it out, I took that photograph that I showed before, but with the the normal ordinary lens, ordinary zoom lens, and it didn't really work on account of these are still too far apart to see them through a finder. So I'm converting it to a smaller finder, which I've ordered, to see how it works. But these are going to get closer together, and I should be able to find them easily in that finder. So that was it. And just to encourage people to go out and take some pictures. So I've actually used my retirement present that I've had for 12 years and actually started using it for astrophotography, which I've only used it for taking pictures of grandchildren before.
What's
So
the
there we are.
date of the conjunction again, please?
The 21st of December. 21st
Right.
of December. But I mean,
Old Christmas Day.
before Christmas Day, it's on the 21st.
No, it used to be called Old Christmas Day.
Oh,
the
Old Christmas Day.
21st.
Yeah, was it?
Yeah,
Okay.
and apparently cattle used to speak on that day.
Oh,
So
really?
folklore says.
Hmm. So yeah, but I mean, anywhere. What I thought was going to be more interesting is to take pictures over the next couple of months as they're getting close together, and just follow it as it goes through, weather permitting, of course.
Yep.
So that's it. My project for the rest of the year.
Steve,
Yeah.
how far away from the sun will they be
Well, I think it's the brightness of the sky that's going to hamper things. It's going to be just about to go over the horizon some hour or so after the sun. So you're going to need a very good view to the west and wait for the sun to go down and then start trying to take pictures. So I think on one day in 10, when we can actually see the sky over the horizon, just go wherever you can, up onto Coombe Gibbet or somewhere and take some pictures. I'm going to have my trees cut too. We're going to phone up the tree cutter next week, and the tops are coming off the trees. So hopefully I'll have a better view. And I will be taking some through the Mead as well, of Mars and Jupiter and Saturn. The Jupiter ones weren't very good, but the Mars one's coming out okay at the moment. So that's me finished.
Okay, and can I say, I'd encourage people to go out and actually just take some of those pictures and bring them along and show us, those, because we've all got a wide range of skills, and it's not all about these, 5-hour images of big objects. It's just about doing the astronomy yourself and getting your own images.
Yeah, that picture I took of the two planets together, that was just put it on a tripod, taking a couple of pictures, make sure it was in the field of view, and then just, first thing I had to do was make sure that the flash didn't come on every time I pressed the button. But once I mastered that, I just took pictures and changed the exposure, and found that 8 seconds worked pretty good. So it's easy to do. Once you've found it, of course.
But I know where you can make your own finder.
I've actually done prepared a little talk to do at the next beginners meeting, just to encourage the beginners to do that. So we got that in a couple of weeks' time, and I asked Nikki if I can have 5 minutes just to show how to make one of these platforms, and with a minimal cost really. Obviously, somebody might have to buy a mounting. You can buy little mounts from on Amazon to mount your camera and lock it with a couple of nuts. That's about £5, and you can buy a finder for £29. So, you know, a 30mm finder, and you can make it. So it was good fun. I enjoyed doing it.
So, just as a matter of interest, that's what I use, which is a red dot finder with a bracket that fits onto the hot shoe of the camera.
Yeah.
And that was about 30 quid all combined. But the good thing with the red dot is you can actually see both Saturn and the surrounding part of the sky, because you're looking at a red dot superimposed on the rest of the sky with the naked eye. So that works quite well.
Yeah, once you've got your shoe on that platform, you can put whatever finder you want on there, can't you?
Well, that is true. Yeah.
So that's why I've done it like that. And in that photograph, all I've done is taken the finder off my 90mm refractor that I take out for general viewing, and I've now actually replacing the 30mm finder that came with a cheap telescope with the 30mm one instead of a 50mm. So I'll use that 30mm on my little mounting, and it will be, I think it's only 5 times rather than 9 times magnification, so I'll be able to get them in a lot easier. But if there's another faint comet, then the 50mm will go back on. That'll make it easier to find again.
Yeah, it's surprisingly difficult to point a DSLR.
It is. When it's a faint object, you can't see it on the screen, so you do really need some kind of finder on there as well. Or you can take a picture and say, I found it in there, so that's all right.
You get lucky.
Steve?
Yeah?
I've got a Starry Night close-up of the conjunction on December the 22nd. Do you want to see it and talk over it?
Well, it'd be the same one. It'd be the same as the one I showed. The last
no, it's a view close-up. How's that?
Oh, I see. Yeah.
9 arc minutes apart. So whether someone could get...
Yeah, because they're moving apart on the 22nd. So mine was on the 21st. I don't know what time it was. I just chose the 21st.
We'll go back a day then. There you go.
Yeah, so they're closest at that point when they're 0.1 of a degree. So what on earth is that? It's 6 minutes, is it?
That's about 6 minutes, yes.
Yeah.
And
so when you think that the moon is 30 minutes in diameter, they're well within the diameter of the moon.
This is 17:58 in the evening, so they will only just have appeared in the twilight before they set.
Yeah. It's going to be awkward to get the picture because it's so low. Going to have to be on top of a hill to take a picture, I think.
You can get pictures of Jupiter, you know, in daylight. So
yeah,
3 degrees 21.
Yeah. But the odd thing about it, from what they're saying, is it's almost going to look like, well, to the naked eye, it's going to look like one object. So you don't very often see 2 planets that close together, do you? And it may even be what the 3 wise men saw 2,000 years ago.
Yep.
There's another talk, which I'm planning to do in the Beginners magazine in December.
I hope you're not spreading rumours.
No, I'm offering no opinion. I'm offering one possible solution to what the star was.
Very wise. Of course, that was in the east, wasn't it? Not the west.
Yeah. Well, actually, I did this on the basis of that talk probably 20 years ago, and I did it a number of places, and I went over as a guest speaker at Farnham. And I ruffled the feathers of one guy there who was saying, that's not the truth, that's not what the Bible says. And he's having a bit of a go at me because I was suggesting it was an astronomical thing rather than an astrological thing. And I tried to walk away from that way. I didn't want to, it was just, I mean, there are lots of different things when you look into that. And you get Starry Night out and you can look at all the different things that are going on. And I came to the conclusion that from a scientific point of view, the double conjunction,